Welcome to our final presentation for Group 2, Project B. Our team members are listed below. In the background, we can see point cloud information that was extracted from Part 3 of the project. Let's go ahead. The outline of the project is Part 1 with AI prompt engineering for flying height calculations, determining how AI can be used, what's the limitations. Part 2 was our stereo model creation from 3 images that were provided there of Colorado Springs, Colorado. The video playing in the background of this slide actually shows the bare earth model that was extracted from those images, or a portion of it anyway. Part 3 was point cloud usage and exploration, where we collected point cloud as well as high resolution imagery from Newark, New Jersey's, around the area of Wake Park, and also from an area in Florida. These parts will be discussed in more detail going forward. Just a general overview, the project explores the various uses for aerial photography and LiDAR point clouds with the purpose of extracting usable information. That information could be terrain models, measurements of features, both natural and man-made, so think roadways, buildings, or topography, calculating distances, being able to show 3D visualizations. All of this information is critical to engineering, environmental, and infrastructure projects. The image here shows the stereo model created from 3 images, meaning that we are able to calculate heights of buildings, see roadways, things like that, with the detail provided. Again, that will be discussed further in Part 2. Our expected outcomes were gaining familiarity with the AirDOS Imagine software, testing the capabilities of current artificial intelligence models in the common calculations, being able to create the stereo models from imagery as seen in the previous slide and discussed further later, sourcing data from public government sources, being able to combine point clouds and aerial imagery, ability to extract and access the information that those images and LiDAR provide us. And then the project overall helped to develop skills in small project planning and project management. Overall, the important thing was to gain a hands-on introductory experience in common photogrammetry uses and some of the software. The image to the left-hand side here is inverted to show some of the bare earth model of the Colorado Springs area.
Hello, I'm Orderly Jermaine, and I'll be presenting part 1 of our project, Flying Height Computation and Error Propagation. This section focuses on calculating the flying height above the terrain using the values given to us and analyzing the uncertainty and error in those measurements using AI. With the provided values, I first converted all units into meters and calculated the photo scale shown here, which resulted in this value. I then used a formula for a vertical photograph and rearranged it in order to find the value of the flying height above terrain, which was 2,205.68 meters. Adding this value and the elevation of A, I got 2,570.68 meters as the value of the total height above datum. This step confirmed the relationship between scale, focal length, and elevation, forming the foundation for later error propagation analysis. Then, our team each compared data generated from different AIs, such as ChatGPT, Copilot, Claude, and Gemini, which each produced nearly identical flying heights, but small differences appeared in the decimal places. For example, here we can compare the results that we got from Claude and Gemini, where the only difference was a 0.89 meter difference. All of these variations come from how AI handles rounding during intermediate steps. Through this, we learned how even such minor rounding can slightly shift the propagated error especially in precision-sensitive calculations like photogrammetry. For example, one AI might round a ratio early, while another keeps more significant digits until the end, and the final results still align within a few meters, but the uncertainty range reflects those subtle behaviors. This comparison helped us understand how computational precision affects real-world measurement accuracy. In summary, the flying height above the terrain was approximately 2,205 meters, with an uncertainty of about 3.48 meters using the parallax method. This part of the project highlights how careful calculation and even the smallest rounding differences can influence the reliability of aerial photogrammetry results. Thank you.
Hi, I am Anasi Zuzi, and I worked on part 2, the Colorado Springs stereo model and terrain extraction. For this part, my teammates and I used ERDS Imagine 2023 to turn 3 overlapping aerial photographs into a 3D model, extract a digital terrain model, and produce orthophotos. I'll walk through the workflow and the accuracy we achieved. The imagery in 3 NAPP frames over Colorado Springs, taken with Zeiss RMKA camera at about 7,000 meters flying height. Reference to the NAD27 Colorado Central Coordinate System. Basically, the workflow runs in 8 stages, and each one depends on the one before it. We started by creating the block, defining the camera from its calibration data, the focal length, and the 8 fiducial marks, and adding the 3 images. Then we solved interior orientation, which ties the image pixel system to the camera's fiducial system. This came out extremely clean, a fiducial RMCE of about 0.16 pixels, which is well under 1 pixel. That actually tells us the foundation of the whole block is solid before we go any further. Next, this is where we start with the exterior orientation. We measured 5 ground control points and 2 checkpoints. The key detail here is that we entered each point's image position directly from the exact pixel coordinates in the project data. Instead of like clicking by eye, it wasn't the easiest, and I tried basically removing the operator pointing errors. The 2 checkpoints were set aside and held out of the solution. They were held out of the solution. So later they could give us an honest, independent accuracy test. After that, we moved on with the orientation measure. Like basically, we ran the bundle block adjustment, the aerial triangulation, it's a hard word to, this solves the position and tilt of all 3 photos at once by minimizing basically the error at every measured point. It converged on the first run with a total image unit, basically weight RMCE of 0.77 pixels. Anything under 1 pixel is strong, consistent results. And that's what we were looking for. That's what we were aiming for. The real test, though, is the 2 checkpoints that the solution never used. Their ground accuracy came out at about 3.7 meters in X 2 meters, in Y, and 5.8 meters in Z. Again, to repeat, basically, the real test that the 2 checkpoints that solution never used, their ground accuracy came out at about 3.74 meters in X, 2 meters in Y, and 5.8 meters in Z. Those numbers are exactly what you expect for this data. The photos are like 1 to 40,000 scale. So a couple meters is on the order of a single pixel, so to speak. The control points themselves weren't really like accuracy to like, they were accurate to 2 meters. So the block can't do better than that. so to speak, and it's performing right at the limit. And the vertical number is larger than the horizontal, which is normal. Elevation comes from a parallel and is always the geometrically weakest direction in the photogrammetry. Yeah, so with that being said, the DTM extraction, this is where the real fun happens. From the triangulated block, we basically extracted the digital terrain model using adaptive automatic terrain extraction. This correlates the overlapping images to compute elevation across the block at about 49 meters cell size, because like the output individual files, we outputted like the individual files, it produced one DTM for each stereo overlap. And finally, we ortho certified all three images using those DTMs, which removes the relief and tilt distortion and gives planimetrically correct ortho photos. Okay, I'm gonna try ahead and say that word again. Planimetrically correct photos. Ortho photos. I did practice it, but I feel like this is the best I'll do. So one thing I ran into, basically each image has to be paired with a DTM that actually covers it. When I first tried the wrong DTM on the last frame, the ERDAS gave an insufficient overlap. I got into panic mode. Basically, I got a warning and produced nothing. So I switched into the correct DTM, fixed it immediately. Yeah, I just took me a minute to figure it out. At the end, the block status table was green across every stage for all three images, and what a sweet feeling it is. The final products were the triangulated block, 2 terrain models, and 3 orthophotos. Overall, the block met the expected accuracy for this imagery, and basically this part gave us a complete working photogrammetric pipeline from raw photos to usable terrain data. And that's basically my 2 cents of it. Thank you so much.
My name is Elijah.
My name is Matthew.
And we will be presenting part 3 of our final presentation on point cloud usage and exploration.
Okay, so this is the overview of the topographical map of the Wecock Park. So for part 3, it mostly focused on modern applications. This included LiDAR and sensor data. And this part was primarily about visualization and accessing high-resolution LiDAR point clouds. So the downloaded portion was the park, obviously, in Peach Palm County. It was located and compiled with point clouds and high-resolution imagery. And all of the data was downloaded and has been placed in a zip folder, and it was shared through the Google Drive, so all the team could access it.
Okay. As for our project workflow, we followed these steps. So we imported the USGS LiDAR point cloud data into the ERDAS image for the Weequahic Park layout. Next, we processed and classified the 3D point cloud data for verification. Then we generated a digital elevation model from the ground points. Then we rendered the topographical map of Weequahic Park to finally get the basic topographical map of Weequahic Park. Some of the technology that we used included the ERDAS Imagine 2023 software, and as stated earlier, the USGS, which stands for the United States Geological Survey 3D elevation program.
Okay, this is the raw point cloud data. This image shows that the area has pretty good coverage of the imagery and point cloud information. The images and point clouds, they overlay nicely on the free base map with the software. And this is without ground control point verification of accuracy. So it's able to be taken from reports provided in data downloads. Okay, so this is the accuracy estimates. And as you can see in this table, we have the overall RMSE, the overall RMSE, so that's X and Y. And then you have the horizontal accuracy and NSSDA. So the report included imagery downloads, we know this already, and the accuracies were computed for the entire 1 foot project. The data was in the UTM zone, that was 18 meters. And the overall RMSEX, as you see there, is about 0.299, and the Y is 0.303. The horizontal accuracy is actually pretty good. That's with 95% confidence at 0.426. And then the NSSDA was with 95% confidence, and that's 0.737. So these were all pretty good measurements.
As for some challenges and delays, one big problem for all of us was processing large amounts of data, as this caused the software to crash multiple times. For some, the information was completely deleted. For some, it was hard to even move to the next step. As for problem 2, some of us experienced difficulties opening the file and converting the display from a 2D view to a 3D view. And this caused, many delays in getting this part of the project done. And here is how we corrected some of those mishaps. One solution we had was exploring whether reducing the project scope to a smaller area would minimize crashes and improve access to other tools within the program. And as for the second solution, importing the point cloud data into a different program could allow or help determine what other products could be developed. Thank you.
Thank you for your time.
And now we will discuss the overall success of the project now that we have went through the 3 parts. An important success was being able to check and each other's work and also have redundancy in the observations and calculations. We see this throughout all the parts of the project. Multiple team members were worked on each part, and that allowed for us to compare and contrast what the results were. Everybody uses slightly different methods and workflows, which allows us to learn from each other's experiences. And again, collaboration and checks are a great representation of real-world methods for ensuring data accuracy. You don't want to rely on just one person to do it all. It's always important to check your work and also have somebody else check your work. AI usage and limitations, being able to use different AI models. We were able to see what the current capabilities are. We did find that the tools are also great at summarizing results of large data sets. So that's a good thing to know going forward, that it may make data more user-friendly or easier to interpret. Demonstrating the need for continued concept and theoretical understanding by humans to properly prompt the AI. However, without background, the AI may or may not get the correct answer if we are not asking the right questions. And knowing the questions to ask comes from background knowledge. Additionally, we were able to locate and access public data. We used 2 tools, the USGS Earth Explorer and USGS LiDAR Explorer tools. While this imagery is free, it isn't the most user-friendly platform, so it does take a little bit of getting used to. Again, this is a great time to explore those sorts of things, then exploring it in the workplace when there is labor costs and things like that. Additionally, being able to process the point clouds, millions, sometimes billions of points that have to be combined and filtered and classified. While it's great that they cover large geographic areas, the processing is definitely both a skill and an art form. It also highlights the need for computing power and large amounts of data storage to be able to work with these, which did bring on some issues for some users, which brings us to our next slide. Some brief mention of drawbacks and hurdles that we encountered. Two big issues were time limitations, and then the software and computing, like the hardware limitations. Not all team members were able to complete or participate in each section. These data sets can be time consuming. Also, NJIT's licensing with AirDOS Imagine requires an active VPN connection, which only works if you have stable high-speed connection, and also assuming that NJIT's end is also working properly. It completely removes the possibility of doing any work in Imagine offline, which can be problematic. Additionally, because of the shortened semester, team formation not happening in the first week did, reduce the amount of time we had to work on the project. There were certain tools in Imagine that seemed to crash more often than others, especially with rendering or when it was doing the heavy computing. Occasionally it would just crash, even when using computers that exceeded the suggested storage and processing requirements. Some of our team members had to go physically to NJIT to use a lab computer, as they were unable to use their laptop with the program, and again, similarly with the VPN linked licensing issues. However, we do have some future ideas for going forward. One idea would be testing limits of data calculation in the AI models. How complex can we make the calculations before the AI is not able to handle it? Or at what point does the extended time that's required for AI processing outweigh the benefits of using that versus a paid software to do these calculations? The other question that we could explore is exactly how much background knowledge would be required to do these calculations. Obviously, through the course, we knew what formulas were supposed to be used, so we were able to check that. But if somebody had no background and they prompted the AI to calculate the flying height, would it be able to do that with no other background knowledge? And then finally, always from an ethical and legal standpoint, where is the accountability in AI, and at what point do we say, hey, AI is just a tool, versus allowing AI to perhaps do most of the work for the project, and where does that fall from a legal and ethical standpoint? Another idea may be exploring other software for point clouds, such as Autodesk Recap Pro. Blender with an add-on is able to actually open point clouds. However, the usage is somewhat limited, especially on the larger size clouds with like geographic data. However, Blender is free, open source. So would it be possible to create tools that were open source for use in something like Blender to process the point cloud software in the way that we need for photogrammetric calculations? If we could do this, this would reduce the entry cost to be able to use point clouds for individuals and small businesses. So those of us who may want to run their own company but use LiDAR, could a open source software be helpful? In conclusion, the overall project provided us with a hands-on laboratory experience. The work provided a well-rounded view of the information that was discussed in the course. Again, kind of going from textbook to hands-on. The skills that we learned throughout this project provide marketable skills for students that are looking for future employers, or those of us that are working. It helps to expand their skill sets and background knowledge, and perhaps incorporate new methods as we go forward. Thank you so much. This was, again, the presentation for Team 2, Project B for summer 2026.